Next up on stage, we have Halepaska, a Ph.D. student under the supervision of Salmaan in School of Architecture, and she will be presenting on passive heat recovery ventilation, a low-carbon solution for building heat loss.
Let's actually start with some good news. We've reduced the average energy requirement for heating and cooling by more than 30% since 2003. Good insulation and airtight construction mean we don't lose heat through leaky envelopes like we used to. And mechanical heat recovery ventilation means we don't lose energy with our warm exhaust air either. It's recovered back into the incoming fresh air instead. But we've created a new problem for ourselves. Mechanical infrastructure, including ventilation ducts, fans, and refrigerants, is now responsible for 20% of embodied carbon emissions during building construction. We're spending carbon to save carbon. Now, we need ventilation to maintain healthy air quality, fresh air in, stale air out. And we need heat recovery to keep from losing energy along with that exhaust air. What we don't need is mechanical heat recovery ventilation. My research uses flow visualizations to investigate a passive alternative, using natural ventilation and some clever architecture. Let's unfold that building on the right. It starts with these three spaces. They share a ventilation stream driven by hot air rising from the chimney. The second room is heated, but the other ones aren't. This generates a cascade of temperatures: cold first, hot second, warm third. Then we just fold the building around itself to loop those cold and warm spaces together. Heat is recovered from that warm exhaust, transferred to the intake through the shared floor. And this is just one potential spatial configuration. There are many, many, many others. I use physical experiments to investigate the thermal performance of these heat recovery loops. The models, like this one, are around 1 meter high, scaled on fluid dynamics criteria so the small-scale flow mirrors that of a full-scale building. Here's the proof of concept. Cold air enters through a basement, rises into a heated space, and is brought back down and through the basement by the chimney. In the control, the space carrying the warm exhaust is insulated. There's no visible heat transfer to the basement, and that exhaust plume is hot. Here's the experiment, where that space operates like a heat exchanger. The exhaust plume is almost 20 degrees cooler than in the control because all that energy is being recovered back into the system. No fans necessary. We spend a lot of money and carbon making buildings comfortable. It's -10 out, and I'm wearing short sleeves. I'd like to keep doing that, but not at the expense of the planet. Designing buildings for natural heat recovery could help, enabling a new form of low-carbon ventilation for heating climates like Canada. Fresh air in, stale air out, but all that energy not going anywhere. Thank you.